So this talk is about reproducibility. So we've had a lot of reproducibility talks over these 2 days. All those presentations or talks I've seen are about how to make your work reproducible by other people, how to make it easy for other people to repeat your work. My presentation is a little bit different. It's about reproducibility, but it is not about how to make your work easy to be repeated by other people. What I'm going to talk is about numerical reproducibility. So that means how to make sure that you get exactly the same numbers, results every time you run your program across different architectures, different environments, right? So this is what this is about. That's a little bit different. So agenda, I'm going to start with a very simple example, a NumPy example, and then describe the problem, and then discuss what kind of solutions we may have. And last, I'm going to talk about the performance, how performance has a role in this, how does it affect performance, and some other information that people can consume offline. So first, just a brief introduction about myself. I work at Intel within a group that developed Intel Mathkernal library. So NumPy, SciPy, we know that they rely on for those linear algebra algorithms. For FFTs, they rely on, for example, BLAS and the LAPACK and the FFTW, right? So people can grab the open source version, like Atlas, like the netlib LAPACK on the open source FFTW, and build into NumPy and SciPy. That's what most people are doing, right? Alternatively, people can also purchase commercial linear algebra packages like Mathkernal library from Intel and link that with your SciPy and NumPy. Okay? The benefit, of course, is just performance. You get a lot better performance. We will see that in a moment. All right, so that put me in the background and explains why I'm here. To be honest, I am not a Python programmer yet, but I've done some work to enable SciPy and NumPy people to build MKL inside their packages. So that's why I'm here. And that's why I think this topic may be interesting to you guys. Okay, let's start with a very simple example. This is probably the simplest Python example in this entire conference, right? It's just a hello world in NumPy. Right, so we have two ND arrays, A and B. Each has 3 elements. This is, of course, a contrived example. But if we look at those 3 numbers, look at them closely. Those are floating point numbers, right? But they are actually 2 to the power of 15 and 2 to the power of minus 15, right? And array B is a little bit different, only in the last element, right? So to make it more interesting, we make the arrays bigger. We just repeat the sequences 1,000 times, right? Okay, so that's a contrived example. So then we do a dot operation on them. What results do you expect, right? So if we can do the dot operation manually using a loop, right? Multiply pairwise and do a sum. And if you do that, it's going to be slow because it doesn't call into the BLAS dot function, right? It's slow. But you can see what kind of result you get. You get 0, right? You get absolutely 0. 0, 0, 0, 0, 0.00. It's just 0, okay? However, if you call NumPy dot, okay, NumPy dot calls into the BLAS function dot, and strange things happen, okay? So we try this on 2 systems. System 1 is blah, blah, blah. Okay, you don't need to worry about those terms, those marketing terms. I just want just want you to know that System 1 is a newer processor. It was just released like half a year ago. But System 2 is a very old, 4-year-old system, 4-year-old processor. This is not the only difference. Another difference is System 1 is a desktop processor, meaning it has only 4 cores. And a second processor, although it is old, but it was a high-end server processor 4 years ago, so it has 8 cores. All right, so let's link MKL into NumPy and run this program and see what we get. Okay, so this is newer processor, this is older processor, both from Intel. And we can see that, well, if we run it just like that, it's not, the results on either system, it's not exactly 0, right? So, and okay, that is fine. It's not exactly 0. We know that. We know computer cannot represent floating point numbers precisely. So, okay, it's not exactly 0. But what bothers people is that they are different, right? So, okay, so we as I said earlier, those two systems have different number of cores, and we know that MKL, the one important reason that it runs very fast, faster than, say, Atlas and open source pack, is because it takes advantages of the multiple cores. So it, by default, spawns multiple threads, right? So for example, on this 4-core machine, it spawns 4 threads and runs in parallel. And on the 8-core machine, it spawns 8 threads running in parallel. So maybe that's the reason, all right? So let's say, let's unify the number of threads. Let's say we just want to run sequentially on both of them. And still we get different results, right? So that means it is a reproducibility problem. And we say, okay, let's say try different things. Let's try set the number of threads, both of them, to 4, and still the same. Results are different. Right? So you guys can actually try. Try what happens on Atlas. And on Atlas, if you use Atlas in your NumPy, you get a different answer, different than either of those. So it is a reproducibility problem, okay? And why results are different on different systems? That is because the root cause is because, I guess everybody knows, floating point computation is not associative. So the order of computation does matter. All right, so here is just some example, a very simple example. Let's say we have 2 to the power of minus 32, plus 1 and minus 1, all right? Depending on how the computation is performed, we can get different answers, either 0 or 2 to the power of minus 63. Both are law-abiding. Both are correct, right? According to standard. So both are correct. So that is the root cause that explains why we saw different results on different machines. Because on different processors, MKL may choose different orders of execution, right? Okay, this isn't news for scientific computing society. When I presented this talk to people in high energy physics, in other traditional high performance computing societies, I got laughed at, right? So what? This is just a part of life. So what? We know that, and we built our whole career, whole life around this, right? Well, it turns out in recent years, there are more and more people are not comfortable with this. There are people with very good reasons asking for bitwise reproducibility, meaning if I run this code today on this machine, I got this result, okay? How about in 5 years, I run the same piece of code with the same input data on a different CPU. I want to get exactly the same result, right? Why this is important to those people? Because of the reasons. a bunch of reasons. For example, technical reason. A lot of projects, a lot of software projects in their testing, in their product validation, they have some gold image or gold results, right? Which is hard-coded. It's just a bunch of digits. And when they do validation, they just compare the computed results with that hard-coded gold bits. And if they are different, then the validation fails. So this is one reason. Another reason is, well, sometimes that makes debugging a little bit difficult. For example, in certain kind of simulation, right? You want to replay the simulation that you did 5 years ago. And sometimes it didn't come out exactly the same. So you're not sure whether it's because some bug introduced in past 5 years or because of something else, right? And another reason is legal reason. So we've got a lot of financial services customers, those big banks, as our users, MKL users. And in those institutions, they have very rigid auditing system. So the auditing system requires them that, well, you did this piece of work today, okay? When we do a 5-year auditing, I want to get exactly the same results as I had today. But in 5 years, the desktop that I ran this work probably is already updated to a newer processor, right? So how do I get the same piece of same result? Shall I go back to the old system? Probably it's no longer available, right? So that's legal reason. And of course, there is customer perception. So a lot of newer generations of computer scientists, they not necessarily have very robust background in floating point computation. So sometimes they just don't get it. So they just don't like the fact that the results may vary from processor to processor. Okay, so these are the reasons. So by the way, this issue is 100% purely about reproducibility. It has nothing to do with accuracy or precision, etc. So like the results we saw earlier, all of those both results are correct, are accurate, right? But they are different. Right? We're not talking about accuracy. We're not talking about machine epsilon, etc. Those kind of things. We're just talking about how to get bit-wide reproducibility. All right. So, as I said earlier, people care about it. And we understand that root cause is because of order of computation. All right? So why do orders of computation change from one system to another? That is because a high-performance library like Atlas, like Mathkernal library from Intel, they do a lot of low-level optimizations. The purpose is to maximize the utilization of those hardware resources. So 3 things here. So for example, instruction sets, right? So from generation to generation, the hardware comes out with newer instruction sets, right? And those instruction sets can be different. For example, the latest instruction set from Intel is called AVX, right? Basically, it has a lot of features, but the most relevant one to this talk is its SIMD width doubled than the previous generation of instruction set. So previously, you can pack, say, 2 double precision floating point numbers in one instruction. You can do one instruction, you can add those 2. You can do 2 adds or do 2 multiplications in one instruction. But with AVX, you can do 4 because you double the SIMD length. So when you vectorize your code, you can pack 4 double precision floating point numbers into one vector. All right. And other reasons multi-cores, multiple processors, when we do threaded execution, then because multiple threads, they may complete at different times, so we don't have a deterministic reduction. Right? Okay. So here is the solution that the Intel Mathkernal library provides. We provide basically a bunch of controls, allow people to control those things, control those factors at runtime. But first thing, you have to fix the number of threads. Now, this is something that we cannot help. So as long as you fix the number of threads, then we have some control. Here is the example. So let's say we still run the same program on these two processors. We fix the number of threads to 4 on both. Then on the newer processor, we get this. We set this environment variable, right, to SSE 4.2. SSE 4.2 is the instruction set that was supported on older processor. So it is supported on both older and newer, right? So by doing that, we unify the instruction set. Oh, okay. Thank you. All right. Thank you. So when we do that, and we see that, well, the results come out identical on both systems. And as long as we keep the same number of threads across these two systems, the numbers are the same. Okay? And here is let's take a close look at those controls. So if you are a performance-oriented person, and you should read this table upward, so from the bottom. So the bottom, the control is called auto. So if you set that environment variable to auto, that means it guarantees you run-to-run reproducibility. So on a single system, from run to run, you get bitwise reproducibility. Then going upward, let's say today you have a newer AVX machine, but you want to be reproducible with an SSE 4.2 machine, then you set both. On both systems, you set environment variable to SSE 4.2, which is exactly the previous example. Then let's say you have one Intel system and one non-Intel system, say AMD system, and you want to get bitwise identical results on both. Then you set the compatible. You set the environment variable to compatible, right? And those are the controls, and those controls give you reproducibility at the price of performance. Right. So looking at this graph, those are the darkest blue bar, that's the performance when this control is not set on an AVX machine. Okay. By the way, the unit here is gigaflops, so the higher the better. So we see the darkest bars are highest. Then next to it, we set only auto. So we say, I don't care about reproducible results across different processors. I just want to get reproducible results from run to run on this processor. So that's auto. That has very little performance impact. And next bars, if we want to have reproducible results on older generation architectures, then we set the environment variable to SSE 4, SSE 4.2, 4.1, and we see the performance drop. Sometimes more than 50%, right? And to put everything in context, the light gray bar on the right-hand side, those bars are Atlas performance, okay? So that set everything in context. Okay, so we call this feature conditional numerical reproducibility. Why conditional? Because it does come with a lot of strings attached. We cannot guarantee identical results in every situation. For example, we do not guarantee reproducible results across operating systems or same results between 32-bit or 64-bit. We don't even guarantee same results when you run different number of threads. And most important thing here is this feature covers only operations that supported in MKL or Atlas or LAPACK. So there are a lot of things outside these packages, right? So for example, you write your own statistics routines, which is not in those LAPACK or BLAST, it's not covered, right? But do not lose hope. What about those floating point computations outside MKL? So say you implement your own thought, right, or something. Well, in that case, Mathkernal library or other Atlas, they don't help. They cannot help. But you can turn to Intel compilers. Intel compilers has some built-in switches that to improve reproducible results from processor to processor and from run to run. Okay, I don't have time to go through those. Just let you know that there are some documentations, articles online, so you can consume offline. So and you can also catch me if you are interested in knowing more about this feature. Okay, and this is my contact information. Okay. Any questions? Yes, please.
So two questions, but the first one is I understand the motivations you put up there, but they all seem largely misguided. Because if you're getting slightly different answers from run to run, then it's really an indication that the true answer is not necessarily what you're getting.
Yes. So the point here is, okay, so the question, so I'll repeat the question first. The question is, if you get different results from run to run, then that may indicate that you are not getting the true result. So my take on this is, well, how do you define true results in the first place, right? So the true result is, if I understand it, it is the result that you can get at infinitely precision. You have infinite precision in your operations, and this is not possible, right? So you really don't get true correct results. You just don't get it. Every floating point computation, you get only approximation, and the quality of this approximation is defined by accuracy. But this is not the point of this talk. This talk assumes your algorithm is good, your hardware is good, your computation gives you a good quality approximation, right? But still, the results vary. Both results I show, both are correct, both are accurate, right? But they are not exactly the same. So we are just trying to deal with that part of problem. Any other questions?
I have one. If I can squeeze in. On the graph you showed where you did get the same results, you had set your OpenMP threads to 1. Would you get the same thing if you used more than 1? Would you get reproducible results with the two others, environmental variable set and, let's say, OpenMP thread numbers to be 2 instead? Would you get the same reproducible results?
Okay, so the question is, on this slide, if I set the number of threads to, say, a different number, 2, right? Do I still get exactly the same results? Right. So the answer is yes. As long as the number of threads is set to be same on both systems.
Got it.
Right.
Okay. Thank you very much.
Could David Lee come up and
Do we have a, okay, go ahead, please.
Do you have any insight into why Intel doesn't open source MKL?
Okay, the question is, why doesn't Intel have open source MKL? I think that is business strategy, which is really far away from my domain and out of my reach. I am a software engineer, so personally, I like open source projects, and I know that Intel has done a lot of things to contribute to open source community. For example, we contribute to a lot to Linux, to glibc, but coming to Mathkernal library, why it's not open source? I really can't, and it's not decision at my level. Sorry.
All right, let's thank Zhang for
Thank you.